Yes, and thank you for inviting me. I think Grant started his talk with I do things differently, and I would start my talk with saying I do things very differently. So today I want to talk about my latest research, which is about generative agent-based social simulation. What that means is I use large language models for decision making within agent-based models. And I'm from Nottingham here, from the computer science department, and mainly I'm interested in using software engineering methods to actually build, design agent-based models in a structured way. As we all have different definitions what agent-based models are, I start with a definition what I understand by agent-based models. So in agent-based modeling, you create a collection of agents. They follow some behavior rules, at least in a traditional agent-based model, and some system properties emerge on the macro level. And agent-based social simulation uses agent-based modeling to investigate social systems. And some topics that people normally look at in social simulation is cohesion or the distribution of social norms, cultural dynamics and modeling cultural differences. We also look at spatial impact. Now, how do I build these kind of models? I define the problem because all models should be problem-based. I identify the active entities, the agents, define their states and behaviors, put them in an environment, establish connections between them, and then I validate my model to make sure that there are no bugs in there. Now, I always had a problem that when I read papers on agent-based modeling, there are very different flavors of agent-based modeling. So I tried to put a table together myself, but I found it very difficult to express the differences. So I actually asked Claude to help me with that. And the distinction I want to make is a typical mathematical agent-based model, a rule-based social simulation agent-based model, which is what I worked on so far, and the new generative large language-driven agent-based model. We don't have to look at the whole table, but what was mentioned before as well is that these different types of models have different purposes. So the primary focus is listed there for the mathematical model to predict disease trajectories, and for the social simulation model to understand emerging patterns, and for the generative agent-based models to explore open-ended social interactions. And one of the big differences is the decision-making mechanisms, and that's what I want to talk about today. And in the mathematical models, we have probabilistic transitions that we are using for decision-making. In the rule-based social simulations, we usually have some explicit rules, like if-then rules, or we use finite state machines for modeling the decision-making. And the finite state machines is what I use. And then in the generative agent-based models, we don't have any rules. We just ask the LLM for a decision. The LLM has a lot of knowledge, so we don't really define rules synthetically, but we let the LLM decide. Then one of the problems is computational costs. So if we solve an ODE, I think it doesn't take a lot of time, at least a simple one, I would assume. If you run a rule-based model with a lot of agents, the time consumption is low to medium. But if you use an LLM and ask for a decision for every agent on every day, it's very costly. So I wanted to choose two examples to quickly go over, and I show you the agent-based modeling version I normally use, and then the generative agent-based modeling version. I have to say this is very early research, so I don't have any outcomes at the moment because I only try to get things working in the first place. For the epidemiology model, I try to model the isolation decision during a pandemic. And you're familiar with these models, but I just wanted to bring them up. So if you have isolation decisions, if you're in a susceptible state, you might think about isolation to not get infected, and if you're in an infected state, you should isolate to not infect others. That's what these diagrams are showing. And now I mentioned state machine diagrams before. As a software engineer, we use these to define how to develop software. And what you can see is the different states that an individual agent can be in. So, you know, an agent can be in state susceptible, infected, or recovered. And it also makes a decision that's behavior related, that it should isolate or not isolate. In this depiction here, we have a rule-based version where you can see that transitions are triggered by rules. And the transitions are the arrows that you can see. Transitions can be triggered by timeouts, by rates, by conditions, which are the rules, or just sending messages between agents. Now the decision-making process, and here we have a rich representation of parameters and data that we use. And as I said before, we have two different decisions to make, once we are susceptible and once we are infected. And you can see that we collect some information about personality traits and environmental observations. But if we make these decisions, for both decisions we need different information. So for the personality traits is how risk-averse an agent is and how much it conforms to rules. And when the agent is infected, we need to think about consciousness and self-efficacy. And then we put a function together that helps making the decision, and the agent will make the decision to either isolate or not. That's the idea of the rule-based system. Now, if we use an agent-based system, everything is the same. The only thing that differs is how we compose our decision-making rules. So they are not really rules, they're prompts. So we use the same information. We have information about a persona, the context this persona is in, and these agents also have memory. So what the previous speaker was saying, it's important to consider memory, and they can memorize their previous decisions. What then happens, I would send information to a large language model like you do on ChatGPT or Claude, and the large language model would give me a decision back. And then I decide to isolate or not. So I have a system prompt that tells the LLM what it should respond, what the format is, and so on. Then I have a main prompt where I define the persona, context, and memory. And usually I also have a validation prompt where actually I send the result from the LLM back to the LLM and ask the LLM to assess what it produced, if that's viable or not. And what I expect the LLM to send me back is clearly a decision, yes or no. So I should isolate I should not. And that decision is based on the persona and the environment. And it should also give me a short reason why. And this is what it looks like actually when you communicate. You can see some text fragments. We don't have time to go through all of this, but there's a system prompt in the top, then there's a user which has a persona, and you can see what's happening in the environment, how many people in range are infected, and that is sent to the large language model and will influence what decision the large language model will send back to me. And you can see in the bottom there, the large language model tells me that based on the persona and the environmental cues, this person would isolate, and it gives a short reason why. Energy systems. So I was considering PV panel adoption and prosumer behavior. This is what the standard diagrams look like. So there's a bus diffusion model, and on the right you can see prosumers in winter not producing a lot of energy and have to buy extra, and in summer they have a surplus of energy that they try to sell. And this is the state chart. So you're a non-adopter, you become an adopter, and then you're self-consuming or you're exporting depending on how much energy you produce. And these models look exactly the same as the models you saw before. They have slightly different inputs, but the functionality is the same. This model also looks the same, so there are a lot of overlaps because we're only talking about decision-making here. And it's similar decisions that we make for isolation or PC one panel adoption. Good, I don't have to show this. So there are some open questions, and these are what kind of experiments do we run? So I get this working now, I get some meaningful responses, but I'm currently stuck deciding how this can be useful. And you can run some sensitivity analysis, you can do testing of the impact of new policies, and you can also do some interesting experiments with prompt validation. But if there's anything else that comes to your mind, I would be very happy to discuss that in the next days. And what can we do with the qualitative output? So we get a lot of returns from the decisions that the LLM makes. And I'm pretty sure there are some patterns in there that might be of interest. So maybe if you have ideas there as well, it would be very nice to see. And one of the things also of interest to the mathematicians maybe is that it would be good to have combined solutions. So we could use a mathematical model because it's low in costs to run it, and then integrate a behavioral model that I just showed you because it's very costly, only use a very small sample size, like modeling 50 people and looking at their behavior, getting the information from the mathematical model into the behavioral model and back to the mathematical model. And I think my time is up. So if you're interested in this, I have a website and I have a blog on there about the agent-based modeling I do. So please go and have a look there. Thank you.